Okay. No, wait, 2? Yeah, 2. So today's the 10th. And before we get to algebra, I want to mention something super exciting in the science world today, and that is that today the first pictures of a black hole were released. Of course, you've got to understand what that means. Of course, you can't see the event horizon of a black hole, but a black hole is such a dynamic and interesting object that you can see the stuff going on around it. It's really incredible. Black holes were theorized to exist, and all the measurements that we could possibly imagine about them were sort of true. All kinds of stuff was true. But before today, a lot of the things were like too wild to believe. The movie Interstellar, if you've seen that, there's in part of the plot, they end up getting close to a black hole, and you're looking at it, and it's like this incredible looking thing. Of course, that's computer generated imagery, but that image of the black hole was made using the equations of general relativity. Sort of like, well, if we have it right, then a black hole ought to, well, in the first place, they ought to exist, and they ought to look like that. And as it happens, the picture released today looks actually pretty similar to that. So that's super exciting. Like, all the science world is like partying today. All right, fine. Good. We've been talking about solving equations. Now, broadly, we're going to break it into 2 categories. So the first category is sort of like the super easy mode category. So this is linear. And you can you can take that as linear is the math name, but as a euphemism, you could say that this is like easy mode. So a couple days ago, not days, but a couple weeks ago, many lectures ago, we already said what a linear equation is, and it took like half a page, and we said everything there is to say about it. So fine. In some sense, I don't need to say any of this, but I'm going to say this to give us a structure to talk about the next thing. So previously, what we said. We said that we would solve the equation ax plus b equal 0 with a is non-zero and a and b constant. So we said that this is a linear equation in one variable, and to solve it takes 2 steps. The first step is we'll subtract b from both sides, so that the resulting equation is ax is negative b. The second step is to divide both sides by a, so that the resulting equation is x is negative b over a. So that's 2 steps. Under every possible circumstance, the first step is possible, because it's always allowed for you to add or subtract the same thing from both sides of an equation. So that's always okay under all circumstances. And then this step, dividing by a, so is division by a always permitted? Is it always acceptable? No, there's a case when it's not okay. So under what case is that? When a is 0. So how do we know for sure that this was allowed?
Because we've already established that a is not 0.
Yeah, because that's what we're saying right there. That's the case we're talking about. We're not talking about another case. Okay. So, you know, there's nothing more to say about that in some sense. But now we're moving into a part of the class where we're going to start solving equations that are, on the one hand, more complicated. So the name for more complicated is going to be nonlinear. And on the other hand, we're also going, in order to deal with that complication, we're going to be looking at these equations from sort of 2 points of view at the same time. One of them is a sort of purely algebraic point of view, and the other one is a geometric point of view. Okay, so we're going to be looking at it from both points of view at the same time. So now what we're going to be asking is this. Now the question is please solve mx plus b equal to k. So mx plus b equal to k. And now this stuff, the requirements, is that m is non-zero and m, b, and k are constant. So on the one hand, algebraically, this is hardly any more complicated than the previous one. It's just there's one more symbol floating around, but that's not a big deal. So algebraically, we take this equation, so mx plus b is k. And we want to solve for x. So, you know, same 2 steps. We'll subtract b from both sides. So mx is k minus b. And then now we'll divide by m. So that we have x is equal to what? What's the right-hand side? Right, so all of this, k minus b over m. So I just wanted to make sure no one was going to, for example, only divide the k, for example, or only divide the b. It's got to be both. So there's like nothing hardly to say, but that's different than this. But now we're going to look at this also geometrically. So what we're going to do is we're going to take this equation, mx plus b is equal to k, and I'm going to say that, well, I'm going to sort of split this equation into two different equations. I'm going to call the left-hand side the red side, so that'll be the red, and then I'll call the right-hand side the green side. So we're going to split this. So into 2 equations. So on the one hand we have y is mx plus b, and y is k. Now, we've talked about these, algebraically what they are and geometrically what they look like already. These are both lines. That's a line, and that's a line. So because we said m is not 0, that means that m is negative or positive. It can't be 0. So this is a line that's either sloping down or sloping up. So this is like, a sloped line that's not horizontal. And what kind of thing is this? So its slope is 0. You could say it like that. And so this would be a horizontal line. So if k was like, 6'3", then you could say, well, here's one, here's one, here's one, here's one, and just everything that's that high. So this This one is a horizontal line. And this is a sloped and non-horizontal line. So we split it into those two parts. And now if I make a sketch, then I'll draw an example of such a red line. So that's y is mx plus b, like that. And then the green one be a horizontal line. And remember, the only meaning of those is that is to say that it keeps going all the way that way, and that it keeps going all the way that way. So now, you know, algebraically, the statement was, here's an equation, solve for x. Okay. Now here's a geometric picture, and here's something different. Now, when I first drew the axis, but I hadn't drawn the lines, you can imagine that we had an axis, and none of the points were given any coloring, so they were all uncolored. Then I drew the red, sort of saying like, well, all of these are red points. Those are all red. And then I drew the green and said, and all of these are green. So then, you know, I could point here and say, well, this point has no color. That point is red. That point there is green. And now the question is that are there any points that received both colors? Are there any points that were colored red and also green? Yeah, exactly this point right here. It was colored red and also green. And I hope you're getting an echo of what we were talking about previously with sets, because what's the name of this point? An intersection. Okay. Now we know the height of that intersection. Its height is what? K. Right? Because all the green points are at height k. So that one's definitely at height k. But the question is how far is it left and right? So which is to say, if I drop this down to the horizontal axis and ask, what is that value right there? Well, what is it? It's some x value. So what I'm saying is I want to be able to say that this is x is equal to, and then I want to fill in this this box. So what goes in the box? You already know the answer. It's literally written on the page. That's what goes in the box. And you know, what I want you to see is that this is sort of really notable, because if you look at this picture, imagine that we keep that red line as it is, so it's fixed. But imagine that we can grab the green line and move it up and down. And imagine that as I'm moving it up and down, this intersection is moving to compensate. So do you observe that I can put the green line anywhere I want, and there's always going to be an intersection. You know, I can't. You know, I can start raising the green line as high as I want. You know, because the red line keeps going all the way up. I can never get the green line above the red entirely. And similarly, going down, there's always going to be a solution. Fine. So now suppose we hold the green line fixed. Then if we keep the slope the same for the red line, we could move it up and down. as long as the slope's the same. There's always going to be an intersection. It's just going to be moving. And if I change the slope of the red line a little bit, there will be a solution. And in fact, as long as the red line has negative slope, even if it's just barely, right? If it's just barely, you know, if the red line, if gravity's going that way, the red line is just almost exactly horizontal, just barely sloped. If it has any slope whatsoever, it's going to eventually hit the green line, even if it takes a long time to get there. But and the same is true if I take the red line and I make it have positive slope, right? Then there's still always going to be an intersection. But if I'm allowed to do anything at all with the red line, move it and change its slope, could we make it to where there's no solution, no intersection? If I'm allowed to do anything at all with the red line, what could I do to the red line to make it to where there's no intersection? I could make it parallel, right? I could make it horizontal and pick it up. But we've already said that it's not permissible for you to make it parallel. Where did we say it's not permissible for you to make it parallel? Right there. That's saying that we're talking about a red line that's not parallel to the green line. The slope is non-zero. It's either going down or it's going up. It is not horizontal. And that's what that is our permission to divide by m. So algebraically, that m not 0 is giving us permission algebraically to divide right there. Geometrically, m not 0 is saying that we're talking about a red line that's not horizontal. Okay, and there's nothing more to say about the linear case. This is like it. There's nothing. That's what I mean by easy mode. There's nothing more to say. So now what we're going to deal with is the nonlinear case. And here, I'll just summarize it with some pictures. So we're still going to want to be interested in solving equations, and algebraically that means performing algebraic operations. Geometrically that means looking for intersections. So all that nonlinear means is that now the red, instead of being flat, all that flat means is that it means straight, like a ruler. So now the red just doesn't have to be flat. It can be bendy. So, maybe something like this. So, so there's something that's bendy. And then we can make, again, the green line's always going to be horizontal. Okay, and then for each one of these, I'll ask the question, what's the number of intersections? Number of intersections / solutions. So how many in this particular case? Just one. Okay, but if I take that same bendy red thing, more or less the same, and I put the green line somewhere else, say like right here. Then now how many intersections? 3 now. Okay. So concerning this picture right here, can you ever achieve 3 intersections for this one if you can put the green anywhere? No, there's only ever going to be exactly 1, assuming that the red can't be horizontal. If the red could be horizontal, you could have infinitely many, because it could be the red and the green line could be the same. So that one has 3. But here's something that's bendy. So that's bendy, like that. it keeps going, you know, all the way up that way and all the way up that way. And then I could put the green line right here. Now how many intersections? None. In the linear case, is it, assuming that the red line must be non-horizontal, can you move the green line somewhere so that there's no solutions? You can't. There's always got to be one. Similarly, we could have, we don't really study this thing I'm about to draw here in our class, but if you take some further math classes, you'll inevitably get to it. So there's something called a sine wave, which is just a graph that goes up and down infinitely many times. So up and down and up and down and up and down. So it does that all the way to the right and all the way to the left. So it's a wave all the way that way. And then I could put the green line like right here. Now, we can only see part of this, but the red keeps going and the green keeps going. How many intersections would there be? Infinitely many. So the nonlinear case is like interesting, right? That's where the interesting stuff is. So the way that we're going to deal with this is we're going to deal with some specific nonlinear cases one at a time. So we're going to say, here's a specific nonlinear case, here's another specific nonlinear case, and we're going to sort of build up a toolbox of very common nonlinear cases. And then once we have enough tools, then you know, we'll start saying, well, here's something that's kind of new, but you've seen enough nonlinear things that you should be able to see what to do from here. You know, it's sort of like, you know, if someone shows you how to build a fence with nails, and then someone shows you how to build a fence with screws, then someone could say, well, we're not using nails or screws, we're using this other kind of fastener. Then you could probably figure it out. So here's the first nonlinear example. Absolute value. So let y be absolute value of x. So first order of business is please fill out this table. So -4, -3, -2, -1, 0, 1, 2, 3, 4. Okay. So, you know, I'm asking you to fill out the table so that each one of those points, when plugged into the equation, the result would be true, which is just, you know, for this one, it's just a complicated way of asking what's the absolute value of -4? 4. So filling all these out, 4, 3, 2, 1, 0, 1, 2, 3, 4. Now, notice that those red numbers are a palindrome, meaning that that sequence of red numbers reads the same left to right and right to left. It's the same. So, you know, that by itself is sort of curious. But the next thing we're going to do is we're going to make a picture. We're going to plot all of those points. And that palindrome-ness, I don't know what the right adjective is. Palindrome-ness? Palindromicity? I don't know. That the palindrome-ness is going to manifest itself in the picture. So if we plot those points, there's a point, ignoring the negative ones for a moment, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, like that. So those all fall on a line, those ones. But then we've got this point, -1, 1, which is right here. like that. And here's where the palindrome-ness becomes apparent, is that every one of these points will have a symmetric counterpart. Is that -1, 1, -2, 2, -3, 3, -4, 4. So you can see that they're paired up. And it's if we were to plot a lot more points and connect the dots and all that, then it would look like this. So the palindrome, this palindrome right here manifests itself in the picture as this symmetry. Neat. Interesting. Okay, so the notable thing I want you to take away from this is that any time that we're dealing with absolute value, if somehow you could bring a picture into the situation, you'd see a V. Somehow there'd be a V somewhere. Now notice that that if this was like enormous and you were a zero-dimensional creature, a point, and this is like enormous and you only like ever lived right there because that's your hometown, then notably it would look like a line to you if this is the only place you ever were at. But then the people on the other side of the universe, they'd be here and it would look like a line to them too. But if you could zoom out far enough, if you could zoom out, then you see, oh, it's actually not a line. It's not a line because that's what a line looks like. Lines don't bend, lines don't have corners. This is not a line. So that is a corner in the sense that no matter if you were there, no matter how close you zoomed in, it would never become round. It would always, at every scale, it would be a corner. So now what we want to do is we want to solve an equation. So here's an example equation. So since this is the first example, it'll be super easy. So absolute value of W is equal to 3. I think it's so funny. The W's and 3's are like the same, except just rotated. Viewing absolute value is kind of like a machine that has inputs and outputs. You could look at this equation as asking, what could we put in into the absolute value as input, so that the output would be 3. -3 would work. If you put -3 in, -3 for input, then +3 would be the output. Is there anything else? 3 would also work. So you could put -3 in, or you could put +3 in. Okay, so there'd be like 2 possibilities. W is -3, or W is 3. Here's so example equations, I guess. So here's another one. So how about absolute value of Z is -5. So now the question is again, sort of viewing it as a machine. The question is, what could you provide as input to absolute value so that the output would be -5? Nothing, right? There isn't a way to achieve that. So there's no solution here. All right. Now I want to sort of stress that this isn't entirely natural, because if we were to walk out to the vending machine over there, Snickers is like a popular candy bar, so it wouldn't surprise me at all if in the vending machine there were like 2 different buttons you could press to get a Snickers. Right? So there's like two slots, and you could say, well, you could press this one or that one. Snickers will come out. But it also wouldn't surprise me if we walked up to the vending machine and you said, hey, I don't want a Snickers. I actually want some fettuccine Alfredo. And then we could look and say, I'm probably going to say, it turns out there's not a button to do that. Okay, well, that's just how it is. So now, to make this work entirely, so now for item 4, suppose that we want to solve the equation absolute value of x is equal to k, where k is a constant. Okay. Then there's going to be exactly 3 possibilities. So I'm gonna do it in columns. So column, 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 like that. So one possibility is that k is a negative number. So k could be negative. Well, but before I do that, before I go into that, I want to do the same splitting here. I'm going to take this absolute value of x is k, and I'm going to say that this is going to be the red part, and this is going to be the green part, and I'm going to split this one equation into 2 equations and say, well, I'm going to consider y is absolute value of x and y is k. And on the previous page we said that the shape of that is a V. So that's a V. And this is a horizontal line. So this one is shaped like that, and this one is shaped like this. So now 3 possibilities. So one possibility is that k could be negative. So in this case, we still have this V here. And y equal to k will be a horizontal line. And where will it be situated on the axis? So what makes you say that? So so we're talking about y is k, and we're taking the particular case when k is some negative value.
Oh, my bad.
So maybe I said positive. I don't know, but I meant negative. So where will the green line be? Yeah, it'll be down here. And so now, I could ask the question. We had an axis. None of the points were given color, and then we said these are the red ones, those are the green ones. Are there any points that, are there any intersections, points that have both colors? None. So the number of intersections slash solutions in this case is none. Okay, fine. The next possibility is so we have an axis here, and we've got absolute value. And now the case k is 0. So again, the green line's horizontal, but now it's going to be in a different place. So where is it? Now it's exactly the x-axis. So I'm going to draw it just barely above, because otherwise you wouldn't be able to see it. But now, same question is that are there any points that were given both colors, red and green, or if you like, is there any intersection? Exactly one, right there at the corner. and its x value is x is 0. All right. Finally, again, we have absolute value. And a green line. And now the horizontal line is above the x-axis. And are there any intersections? Yes, of course. And then how many? Those two. So now there's two solutions. And what specifically we are interested in is that what is the height of those 2 points? How tall are they? What height are they at? Well, it's definitely positive. And in particular, from the picture, we could say, oh, they're at height k. So they're both at height k. So that's not interesting to us, but rather the thing that we're interested in is that what is their x values? So what's that value right there?
3.
Sorry?
Like probably 3.
Well, if k was 3, then yeah, that'd be 3, like the previous picture.
I mean, probably K.
Yeah, but so for this one, it'd be just k. Right? What's that one?
Negative K.
Negative k. So, taking all of this together, what this is saying is that if we have an equation like so, there's 3 possibilities. So here's the geometry of it, and here I'll do an example of each one. So an example equation here could be something like, example. Could be something like, please solve absolute value of, like we did on the previous page, absolute value of z is -5. So what's the correct response to that? No solution. Because you're asking something like, how many times do the red and the green intersect? No times. Here, an example of this one would be something like, something like the absolute value of p is equal to 0. Well, and what's p? 0. P couldn't be a positive number because if you put a positive number in the absolute value, a positive number would come out. So it couldn't be 0. And p couldn't be negative because if you put a negative number into the absolute value, a positive number will come out. So this is the only possibility. And then for this one, like the previous page, would be something like absolute value of w is 3. So what input could you provide to the absolute value so that the output would be 3? Right, 2 possibilities. All right. So finally, for now, some things are notable because they're there, and some things are notable because they're not there. So, if there was someone in a Velociraptor suit standing right over there, that'd be notable. Someone ought to ask, like, hey. But sometimes things are notable because they're not there. So there's if you've seen this kind of thing before, then notably I am purposefully not saying something. And there's a symbol that's very commonly used in this part, and it's written. Its name is plus or minus, and then it's written as a plus sitting on top of a minus. And for now, the use of plus or minus is prohibited. So I promise I have a good reason for that. Prohibited. If you have if you're not sure what that is, don't worry. You won't use it on accident if you don't already know what it is. All right. So let's have an example. Solve a typical example of this. So please solve the absolute value of 2y minus 5 divided by 9, all of that in absolute value. I don't know, plus 4 is equal to 10. All right. And we want to solve it for y. So the first thing to do, the strategy, because there's absolute value in it, it's got absolute value like that. We want to get it into the form that looks like this. That looks like absolute value of x is equal to k, where we've just got all the absolute value business on one side and then equal to constant on the other side. That's the form we want to get it into. So taking this, absolute value of 2y minus 5 over 9 plus 4 is 10. So how can we achieve that? Yeah, move the 4 over. Okay, so then subtract 4, subtract 4. So now it reads absolute value 2y subtract 5 over 9 is 6. So now we have it into that form. And now the strategy is that we need to categorize which one of these we're in. So, there's 3 possibilities. And the question is which one do we find ourselves in? That one, right? So it's that one. Now, if you're not a picture person, that's fine. In my mind, when I imagine doing this in my mind, it's all pictures. But alternatively, you can look at it like this and say, all right, I'm going to cover up the input to the absolute value. So I'm just going to cover it up, and then I'm going to ask, okay, in principle, is it possible for me to provide an input to the absolute value so that the output would be 6?
Yes.
Yeah. In fact, we can do it in 2 ways. What 2 ways? Yeah. If we could make the input -6, that'd work. If we could make the input +6, that would work. So we're going to take this equation, which is nonlinear. It's nonlinear. And we're going to break it into 2 equations. So one possibility is that the input, 2y minus 5 over 9, it could be -6. That's possible. The other possibility is that 2y minus 5 all over 9 could be +6. So we took this nonlinear equation and we broke it into 2 pieces. Now that's that's bad because now we have twice as many equations. So that's not great. But each one of the equations is simpler. So we increased the number of equations. That was the cost. And the benefit is that these equations are simpler. So specifically, if we ignore this one over here and just look at this one, if we wanted to solve this equation, what would we do? Yeah, multiply by 9. So if I do that real quick, then I'd have 2y minus 5 is negative 54. And now, if you hadn't already identified it, here's an equation. This is a linear equation. So this is like the easiest kind of equation that exists. So we took a nonlinear equation and broke it into two different linear equations. Great. So 2y minus 5 is 54 like this. And now we can add 5. So 2y is, so adding 5, that would be what? Negative 49. Or 2y is 59. And then divide by 2, y is negative 24.5. Or y is 29.5. Interesting. Any question about this one? Okay, let's have another one. So, so solve. Absolute value of 4x minus 7 divided by 3, and then maybe I'll put a 2 on the outside here, so there's a 2 there now. So 2 times that, and then plus 10, and then is equal to something else nice, like I already used a 7, so I'll put a 5. Why not? Just go there. All right. So again, so I want you to work on this one and get it to this to this point and proceed, but please hold your comments so everyone gets an opportunity to get to the decision point. Oh, we're almost out of time, so I'm going to keep going. So, you know, we want it to look like this. We want to get it there in that form. So I'll move the 10 over and obtain 2 multiplied by absolute value of 4x minus 7 over 3 is equal to negative 5. And then now I'll divide both sides by 2 so that we have absolute value 4x minus 7 over 3 is negative 2.5. All right? So now what? So we break it into 2 equations. Okay, why do we break it into 2 equations? And what 2 equations? Yeah. Yeah, so there's no solution, right? So then, from the point of view of categorizing it into the 3 possibilities, again with these 3 possibilities, 1, 2, 3, which one are we in? The first one, in fact. We're in the first one. Because, you know, this is the case, you know, for algebraically when the right-hand side is negative, when the right-hand side is 0, when the right-hand side is positive, algebraically. Now, if you're, you know, if you don't like the picture, then you can view it like this. You can say, well, I've got an absolute value there. And in principle, is it possible to provide an input to the absolute value so that the output would be negative 2.5? And the answer is no. There isn't one. Just like you can't get a fettuccine out of the thing over there. There just isn't. There's just not a button. So there's no solution. Nevertheless, I will mention that the most common error for students to make is to do exactly this, is to say, well, this, that bit without absolute value could be negative 2.5, or, that bit without absolute value could be positive 2.5. That's the most common error. But that's the same as saying that, looking at this, I think that there's two intersections. But there's really not. So now, in the 30 seconds left, I want to just foreshadow what we're going to do next time so that you can be thinking about it. So the next nonlinear thing that we're going to deal with is a parabola. It's a parabola. Its shape is similar to absolute value. So it's sort of like a V, except it's bendy and it's smooth at the bottom. But it's V-ish. And we are also going to find that there are 3 cases. And geometrically, this shape, the name of this shape is parabola. We've plotted one previously. So this is a parabola. Algebraically, the name of this thing is a quadratic. And we're going to, in all the cases, figure out a way to see that, in this case, no solutions. In this case, 1 solution. In this case, 2 solutions. And we're going to come up with a formula to solve this equations that have quadratics in it. And what's going to be the name of that formula?
Quadratic line and something. Quadratic formula.
The quadratic formula, because that's how stuff gets named in math class. All right, that's all that we have for today. I hope you have a wonderful Wednesday.